Radio frequency identification is the wireless use of electromagnetic fields to transfer data. For the purposes of automatically identifying and tracking tags attached to objects, the tags contain electronically stored information. Some tags are powered by electromagnetic induction from magnetic fields produced near the reader. Some types collect energy from the interrogating radio waves and act as a passive transponder. Other types have a local power source such as a battery and may operate at hundreds of meters from the reader. Unlike a barcode, the tag does not necessarily need to be within line of sight of the reader and may be embedded in the tracked object. RFID is one method for automatic identification and data capture. RFID tags are used in many industries. For example, an RFID tag attached to an automobile during production can be used to track its progress through the assembly line. RFID-tagged pharmaceuticals can be tracked through warehouses, and implanting RFID microchips in livestock and pets allows positive identification of animals. Since RFID tags can be attached to cash, clothing, and possessions, or implanted in animals and people, the possibility of reading personally linked information without consent has raised serious privacy concerns. These concerns resulted in standard specifications development addressing privacy and security issues. ISO, IEC 18000 and ISO, IEC 29167 use on-chip cryptography methods for untraceability, tag and reader authentication, and over-the-air privacy. ISO, IEC 20248 specifies a digital signature data structure for RFID and barcodes, providing data, source and read method authenticity. This work is done within ISO, IEC JTC1, SC31 automatic identification and data capture techniques. In 2014, the world RFID market is worth $8.89 billion, up from $7.77 billion in 2013 and $6.96 billion in 2012. This includes tags, readers, and software, services for RFID cards, labels, fobs, and all other form factors. The market value is expected to rise to $27.31 billion by 2024. History. In 1945, Eliakut Onemin invented an espionage tool for the Soviet Union which retransmitted incident radio waves with audio information. Sound waves vibrated a diaphragm which slightly altered the shape of the resonator, which modulated the reflected radio frequency. Even though this device was a covert listening device, not an identification tag, it is considered to be a predecessor of RFID, because it was likewise passive, being energized and activated by waves from an outside source. Similar technology, such as the IFF transponder, was routinely used by the Allies and Germany in World War II to identify aircraft as friend or foe. Transponders are still used by most powered aircraft to this day. Another early work exploring RFID is the landmark 1948 paper by Harry Stockman. Stockman predicted that considerable research and development work has to be done before the remaining basic problems in reflected power communication are solved, and before the field of useful applications is explored. Mario Cardullo's device, patented on January 23, 1973, was the first true ancestor of modern RFID, as it was a passive radio transponder with memory. The initial device was passive, powered by the interrogating signal, and was demonstrated in 1971 to the New York Port Authority and other potential users, and consisted of a transponder with 16-bit memory for use as a toll device. The basic Cardullo patent covers the use of RF, sound and light as transmission media. The original business plan presented to investors in 1969 showed uses in transportation, banking, security and medical. An early demonstration of reflected power RFID tags, both passive and semi-passive, was performed by Stephen Depp, Alfred Coel, and Robert Freeman at the Los Alamos National Laboratory in 1973. The portable system operated at 915 MHz and used 12-bit tags. This technique is used by the majority of today's UHF-ID and microwave RFID tags. The first patent to be associated with the abbreviation RFID was granted to Charles Walton in 1983. Design. Tags. A radio frequency identification system uses tags, or labels attached to the objects to be identified. Two-way radio transmitter receivers called interrogators or readers send a signal to the tag and read its response. RFID tags can be either passive, active or battery-assisted passive. An active tag has an onboard battery and periodically transmits its ID signal. A battery-assisted passive has a small battery on board and is activated when in the presence of an RFID reader. A passive tag is cheaper and smaller because it has no battery. Instead, the tag uses the radio energy transmitted by the reader. However, to operate a passive tag, it must be illuminated with a power level roughly 1,000 times stronger than for signal transmission. That makes a difference in interference and in exposure to radiation. Tags may either be read-only, having a factory-assigned serial number that is used as a key into a database, or may be read-write, where object-specific data can be written into the tag by the system user. Field programmable tags may be write once, or read multiple. Blank tags may be written with an electronic product code by the user. RFID tags contain at least two parts: an integrated circuit for storing and processing information, modulating and demodulating a radio frequency signal, collecting DC power from the incident reader signal, and other specialized functions, and an antenna for receiving and transmitting the signal. The tag information is stored in a non-volatile memory. The RFID tag includes either fixed or programmable logic for processing the transmission and sensor data, respectively. An RFID reader transmits an encoded radio signal to interrogate the tag. The RFID tag receives the message and then responds with its identification and other information. This may be only a unique tag serial number, or may be product-related information such as a stock number, lot or batch number, production date, or other specific information. Since tags have individual serial numbers, the RFID system design can discriminate among several tags that might be within the range of the RFID reader and read them simultaneously. Readers' RFID systems can be classified by the type of tag and reader. A passive reader active tag system has a passive reader which only receives radio signals from active tags. The reception range of a Pratt system reader can be adjusted from 1–2000 feet, allowing flexibility in applications such as asset protection and supervision. An active reader passive tag system has an active reader, which transmits interrogator signals and also receives authentication replies from passive tags. An active reader active tag system uses active tags awoken with an interrogator signal from the active reader. A variation of this system could also use a battery-assisted passive tag which acts like a passive tag but has a small battery to power the tag's return reporting signal. Fixed readers are set up to create a specific interrogation zone which can be tightly controlled. This allows a highly defined reading area for when tags go in and out of the interrogation zone. Mobile readers may be handheld or mounted on carts or vehicles. Frequencies signaling between the reader and the tag is done in several different incompatible ways, depending on the frequency band used by the tag. Tags operating on LF and HF bands are, in terms of radio wavelength, very close to the reader antenna because they are only a small percentage of a wavelength away. In this near-field region, the tag is closely coupled electrically with the transmitter in the reader. The tag can modulate the field produced by the reader by changing the electrical loading the tag represents. By switching between lower and higher relative loads, the tag produces a change that the reader can detect. At UHF and higher frequencies, the tag is more than one radio wavelength away from the reader, requiring a different approach. The tag can backscatter a signal. Active tags may contain functionally separated transmitters and receivers, and the tag need not respond on a frequency related to the reader's interrogation signal. An electronic product code is one common type of data stored in a tag. When written into the tag by an RFID printer, the tag contains a 96-bit string of data. The first 8 bits are a header, which identifies the version of the protocol. The next 28 bits identify the organization that manages the data for this tag. The organization number is assigned by the EPC Global Consortium. The next 24 bits are an object class, identifying the kind of product. The last 36 bits are a unique serial number for a particular tag. These last 2 fields are set by the organization that issued the tag. Rather like a URL, the total electronic product code number can be used as a key into a global database to uniquely identify a particular product. Often more than one tag will respond to a tag reader. For example, many individual products with tags may be shipped in a common box or on a common pallet. Collision detection is important to allow reading of data. 2 different types of protocols are used to singulate a particular tag, allowing its data to be read in the midst of many similar tags. In a slotted aloha system, the reader broadcasts an initialization command and a parameter that the tags individually use to pseudo-randomly delay their responses. When using an adaptive binary tree protocol, the reader sends an initialization symbol and then transmits 1 bit of ID data at a time. Only tags with matching bits respond, and eventually only one tag matches the complete ID string. Both methods have drawbacks when used with many tags or with multiple overlapping readers. Bulk reading is a strategy for interrogating multiple tags at the same time, but lacks sufficient precision for inventory control. Miniaturization RFIDs are easy to conceal or incorporate in other items. For example, in 2009 researchers at Bristol University successfully glued RFID microtransponders to live ants in order to study their behavior. This trend towards increasingly miniaturized RFIDs is likely to continue as technology advances. Hitachi holds the record for the smallest RFID chip, at 0.05 mm times 0.05 mm. This is 1/64th the size of the previous record holder, the Mu chip. Manufacture is enabled by using the silicon on insulator process. These dust-sized chips can store 38-digit numbers using 128-bit read-only memory. A major challenge is the attachment of antennas, thus limiting read range to only millimeters.